G'day. In this video, we're going to be unpacking two phenomena which are closely related to sound energy and sound waves, and that is beat and the Doppler effect. So we're having a look at our final dot point of this inquiry question, still looking at evidence suggesting that sound is a mechanical wave. This dot point in particular is looking at the qualitative and quantitative analysis that we undertake when looking at the nature of sound in scenarios where beats form or we observe the Doppler effect. So our aim today is to introduce both of those concepts, and there's also going to be a practice calculation included as well to demonstrate how we can show the quantitative relationships present in the Doppler effect. So first off, let's unpack beats. Essentially, a beat will form when we have the superposition of two sound waves with frequencies that are quite close to each other. When we have sound waves of similar frequencies superposing over the top of each other, we end up forming something that we call a wave envelope, which essentially are these dotted lines that we see represented in the diagram. So when we have these two waves over the top of each other and we end up with our resultant, they usually look something like this. Essentially, we have a consistent frequency, but we have changes in the amplitude of the wave. We have already discussed in previous videos that changes in amplitude of a sound wave will result in perceiving differences in volume. So what that means is when there is a beat between two sound waves, we'll end up hearing a difference between the two of them by this fluctuation that we have in the volume. And the rate at which we hear that fluctuation in volume essentially is the beat frequency. When we're talking about the beat frequency, we're referring to the number of oscillations in volume per second. There's actually this really nifty relationship between the frequencies that are superposing and the beat frequency that they produce. Essentially, if you subtract one of those frequencies from the other and ensure that the number is positive, so these straight lines that go up and down essentially is an absolute value, meaning that whether you're doing big number minus small number or small number minus big number, you will end up with a positive number. But yeah, you essentially subtract these two frequencies from each other, and the positive value is the beat frequency. So for example, if one of the frequencies was 60 and the other frequency was 58, you subtract 60 from 58 hertz and end up with a beat frequency of 2 hertz. What that would mean is that you would observe 2 oscillations in volume every second. We'll do a couple of extra practice questions in class and also try and observe some beats as well. The other concept in this video is a little bit more complex than beats. This is the Doppler effect. Most commonly, we associate the Doppler effect with the sound of a passing vehicle. Now, this observation can be explained by thinking about the point of view of two different observers. So I'm going to draw an orange observer who is currently in front of the fire truck in this diagram. And I'm also going to draw another observer who is behind the truck. Our orange observer has a truck approaching them, and the green observer is going to have the truck moving away from them. The truck is emitting a sound at a set pitch. In other words, a set frequency. That would be their siren. However, the green and orange observers are not going to perceive or observe the pitch of the siren to actually match the pitch that is being emitted. The person in front of the truck, where the truck is approaching them, is going to observe a higher frequency, therefore a higher pitch. And the person behind the truck, where the truck is moving away from them, the person in green is going to observe a lower frequency or a lower pitch of the siren. And this is because sound is traveling in all directions, but so is the truck. So if the truck is moving towards the waves that have been emitted, the waves are actually compressed upon each other, and the wavelength of the wave that was originally emitted is shortened. With a shortened wavelength, assuming that the speed of sound is constant in this scenario that we're talking about, we can then conclude that the frequency will decrease. Thus, again, a higher observed pitch. On the other side, though, we have sound being emitted from the siren, but as the truck moves away from its original position, the sound waves essentially are extended. The wavelength increases. And as a result, again, assuming that velocity for the sound is constant, then that will also decrease the frequency, resulting in a lower pitch observed by our person in green. This relationship is shown in the equation in our data sheet. It says F dash, which represents the observed pitch, is going to be equal to the pitch or the frequency emitted by the source, but multiplied by this term here, which takes into account all possible velocities, the velocity of the wave to begin with. So in our case, that would just be 340 meters per second. That's just the speed of sound, but it also takes into account the velocity of the observer and the velocity of the source. Now, something that's a little bit tricky about this equation, though, is there are actually two equations, and it depends on whether you are an observer who is moving towards a sound source or you're an observer that is moving away from the sound source. Effectively, the structure of the equation remains the same, but the pluses and minuses for the observer on the numerator and the source on the denominator actually flip depending on whether or not the observer is moving towards or away from the original wave source. So the equation displayed in your data sheet allows you to calculate for the observed frequency for an observer who is moving towards the wave source. However, as I mentioned before, if we have a scenario where the observer is moving away from the wave source, the equation will look like this. So again, the structure of the equation is identical. The only difference is that the plus and minus symbols are inverted. And this is something that you will need to remember and apply for any problem that involves the Doppler effect. So let's apply both of those equations now. So a car is traveling past a stationary observer at 25.1 meters per second, and the car engine emits a sound at a frequency of 953 hertz. We're being asked to calculate the frequency heard by the observer, one, as the car approaches, and in the second calculation, when the car has passed. So in the scenario where the car is moving towards the observer, we are expecting a higher pitch, which means that the resulting frequency that is observed should be greater than the emitted frequency, so greater than, in this case, 953 hertz. On the flip side, when the car is moving away, we're expecting a lower pitch. So for both scenarios, I'm going to write down the appropriate equation and substitute accordingly. Note that in both of these solutions, the velocity of the observer is 0. We're told that the observer is stationary. Thus, this numerator is simply going to be the speed of sound. However, the denominator, the distinct difference is that either the velocity of the car is being subtracted from the speed of sound or it's being added onto. That's essentially the only difference in both of these equations. So once those values are substituted in, we get results of 1029 hertz and 887 hertz respectively. It's important to note here that we should really be checking whether or not our conceptual understanding of the Doppler effect matches our quantitative calculation. So we said before that if the car was moving towards the observer, we should expect a higher pitch. In other words, a frequency greater than 953 hertz. That's exactly what we get here. If we use the incorrect equation, we'd be getting a number that was less than, meaning that we may have used the wrong equation. And that's always something that's really effective to reflect on when doing a calculation for the Doppler effect, because really your biggest mistake here is going to be using the incorrect set of addition and subtractions on your numerator and denominator. So if you are getting an answer that you don't expect to be correct, it probably means that you need to do the solution just flipped around the other way. And then obviously because this value is lower, that's exactly matching what we were expecting here, suggesting that our solution for away is correct as well. Thank you very much. In the next video, we're going to move on to inquiry question 4, which is looking at phenomenon associated with light. Our focus is going to be on reflection, refraction, and total internal reflection. Until then, have a good one.